Okay, well, today we're going to learn how to do calculations for cubic cell arrangements. We've talked about body-centered cubic, face-centered cubic, and basic cubic. And when we do these calculations, vitally to understand the geometry of these cells. So we're going to deal only with simple crystal structures. We're going to deal only with monatomic metallic cubic crystals. So crystals of silver or gold or copper, just to keep it basic. Now, all angles in our cells will be 90 degrees, and I'm going to refer to the side length as the letter A. And of course, these will be perfect cubes. So the volume of this would be A times A times A. Now it becomes important to understand the relationship between the diagonal length of the face and the diagonal from one side of the cube to the other. We're going to be using those to calculate the radius of atoms in these unit cells. And I will show you the math involved, and we'll get to those problems in a minute. So now, if you can imagine this triangle that goes from diagonal to diagonal, if you could flip it up, it is still a right angle triangle. So now when we're looking at a face, we're talking about, of course, one of the 6 faces of this cube. We know through Pythagorean theorem, there's a relationship between the length of this diagonal on a face and the length of the actual cube, the dimensions of the cube, A. We know, for instance, that if we square B, it's going to equal to A squared plus A squared. So we can add those two A squareds together and we get 2A squared. And now if we wanted to find B, we could take the square root of both sides. So the square root of B squared is B, and the square root of 2A squared is the square root of 2 times A. Now, I'm going to deal with the second triangle. The second triangle is the triangle that goes from one corner of the cube to the other corner of the cube. We're going to call that dimension C. And again, we're going to flip this triangle straight up. And we know the relationship between that diagonal C from one end of the cube to the other, and A and B being the diagonal of one of the faces of the cube. So again, Pythagorean theorem leads us to the C squared, the hypotenuse, is equal to A squared plus B squared. Well, we've already established what B squared equals. B squared equals 2A squared. So it gives us a relationship between B squared and A squared. So I'm going to substitute that in this equation. So instead of B squared, I'm going to say it's really 2A squared. So now, just to show you the relationship where it came from, we can get a relationship between C and A. So C squared really equals 3A squared. C being the diagonal that goes from one end of this cube to the other end of that cube. So if we take the square root of both sides, we get the square root of C squared is C, and the square root, of course, of 3A squared is A times the cube root of 3, or cube root of 3A. Either way, you can write it. So there's the simple math we're going to be using to solve these problems. So now, when you're dealing with a body-centered cubic structure, C, that diagonal we just talked about, is really equal to 4 times the length of atoms. It's the radius of atoms. And I'll show you that relationship by looking at this diagram. Again, a body-centered cubit has an atom in the middle, and we have these 1/8 of atoms at each corner. So that if I wanted to show you C, for instance, which is the distance from one diagonal to the other, we can see that C really equals, here's one radius of an atom. The second is the radius inside the large atom in the middle. The third is the radius on the other side of that atom. Then the fourth is the radius of this atom at the corner. So we really deal with 4R. So what that gives us is a relationship between this diagonal and the atoms inside this body-centered cubic cell. Now, let's talk about face-centered cubic cells. If I have a face-centered cubic structure and I have a diagonal that goes from here to here along the face, here to here, I could show it. We're going to call that again B. And you can see that there is a relationship now for a face-centered cubic structure, a face-centered cubic cell. There's a relationship between the radii of the atoms and B. We can say again, there are really 4 radii of atoms here. One there, one there, one there, and one there. So 4R really equals that length of diagonal B. And we can rearrange this equation to get it what the radius of the atom is. The radius of the atom is equal to that diagonal divided by 4. Okay? So those are, again, the basics. So we're going to talk about the cell densities and the packing factors of these various crystals. So cell density can be calculated using the formula for density, which is mass divided by volume. We can use this simple symbol here to represent density. So the density is mass divided by the volume. Now we can find the mass of a number of atoms by taking the number of atoms and finding the mass of one atom. So we can find the mass of one atom by taking the molar mass and dividing it by Avogadro's number, which is the number of atoms in a mole. Remember, the molar mass is given as grams per mole. So when we divide the grams per mole by the number of atoms in a mole, we get the number of grams in one atom. And then if we know the number of atoms that are found in that particular unit cubic cell, then we can figure out the mass of the atoms in the cubic cell. And the volume, of course, we talked about how the dimension that we're looking at for the cubic cell, a dimension is A. So the density of the substance is equal to the density of the unit cell. So again, these are what these symbols mean: the molar mass, Avogadro's number, number of atoms per unit cell, and the cell parameter. So the packing factor, of course, is the volume of the atoms in that cubic cell divided by the volume of a unit cell. And that is a packing factor. So I'm going to show you a problem how to solve for those things. So these are the mathematical relationships we're going to use to solve our problems. So we know the volume of atoms is 4/3 pi r cubed times the number of atoms in the cubic cell divided by, of course, the volume of a unit cell, which is A cubed, the dimension being one of the 3 dimensions of that cubic cell. They're all going to be the same. So here's a typical problem that you could be asked to answer. So this would be on your final exam, a type of question. So we could say copper has a density of 8,930 kilograms per cubic meter and forms a face-centered cubic crystal. So let's show how we calculate the mass of a unit cell of copper. So again, since it's a face-centered cubic cell, here is what it looks like. They're face-centered means there's an atom on each face. There's 6 faces, and there's also 1/8 of an atom at each corner. There's 8 corners. So we've been given the density, mass divided by volume, and we look up what the molar mass of copper is. It's given as 63.55 grams per mole on your periodic table. So now we can find the mass of an individual atom. We can say, well, we know that one atom has a mass of 63.55 grams, and we know there's 6.02 times 10 to the 23 atoms in a mole. So when we cancel the mole units and divide 63.55 grams by 6.02 times 10 to the 23, we get the mass of a single atom. Now, this cubic cell has more than one atom, doesn't it? The cubic cell, if it's face-centered, again, there is 1/8 of an atom in each corner, and there's 8 of them. And of course, the face-centered, at each face, there's 6 faces in this cube. each face has half an atom. So 6 times a half is 3, and 8 times 8 is 1. 3 added to 1, 4 atoms. So this particular unit cell of a face-centered cubic crystal has 4 atoms. We know the mass of one atom, 1.056 times 10 to the minus 22 grams. So if we multiply by 4, we end up with the mass of this unit cell of copper, given this density. That's the first calculation. Now the second calculation, we're going to show the volume of the unit cell. We're going to have to calculate A. Remember, it's A, the 3 dimensions of our cube. It's a perfect cube. So we know mass is that many grams per unit cell. We know the density, which was given to us. So we can rearrange the density equation. So we know the volume of a cell is really mass divided by density. This is the same equation rearranged for volume. So we know the mass. We've calculated the mass of a cell. Okay, the mass of those atoms in the cell. We calculated that. That was the mass of 4 atoms, remember, because there's 4 atoms in here. And we know, for instance, there's 1,000 grams in a kilogram. And we know there's a cubic meter, in this case, for every kilogram. So when we cancel, we end up canceling the grams and the kilograms. We divide 4.233 times 10 to the minus 22 by 8,930, and then we also divide by 1,000. And we end up with the volume of this face-centered cubic unit cell. Now let's calculate the lattice parameter. The lattice parameter is what I talked about. It's, again, the dimension of the cube, each side of the cube. A, we call it. So how long is A? Well, we know A is really the cube root of the volume, because A times A times A equals the volume. We take the cube root of each side, we get A is equal to the cube root of the volume. Well, we just figured out the volume of this unit cell. So if we take the cube root of the volume, we now know what A is. It's 3.616 times 10 to the minus 10 meters. So we've calculated the lattice parameter. Next question I'm going to answer, calculate the radius of the copper atom. So the radius of the copper atom. Again, we know the length of A, and we know, since it's face-centered cubic cell, we know that 4r, remember 4 radii, equals the length of this diagonal. So the diagonal face is 4r, and recall that we did that calculation. We could say the relationship between b squared equals a squared plus a squared, equals 2a squared when we add those up. So b is the square root of 2 times a. So we know the 4r is equal to the square root of 2 times a. Well, we calculated the radius of the atom. The radius of the atom is the root of 2 times a divided by 4. So we get the radius of the copper atom. Because we know the relationship again between the unit cell, how many atoms go across this diagonal, we can calculate the radius of each copper atom. Now we're going to talk about the octahedral holes, the spaces between these atoms when they're packed tightly. Well, we can see that the distance from here to here is what we call the diameter of this hole, this octahedral hole. There's 8 of these octahedral holes situated around this particular crystal structure. So we know that A, the dimension from here to here, is really equal to R plus DH. So now we can rearrange the equation and say the diameter of the hole is really A take away 2R. So we know what A is. We calculated it, 3.616 times 10 to the minus 10 meters. And we know R. We calculated it as 1.278 times 10 to the minus 10 meters. So we can now calculate the diameter of that octahedral hole. So we simply subtract this quantity from this quantity. And there is the diameter of my hole in a crystal of copper, which is face-centered cubic. Now we're going to calculate the packing factor. The packing factor is the volume of atoms divided by the volume of a unit cell. Now we knew there were 4 atoms packed in here. So we know the volume of an individual atom is 4/3 pi r cubed. So we're going to multiply the 4/3 pi r cubed. We calculated the radius of the atoms. There's 4 of them. We divide by the dimension A cubed, and we get a value of 0.740. Again, this is unitless because the units cancel. And that is the packing factor, the most efficient way to pack crystals, atoms in a crystal, or packing anything really. Now, let's just move this to read the next question here. So let's say we have silver and it forms a crystal that's face-centered cubic again. The radius of a silver atom is 144 picometers. Now remember what a picometer is. It's 10 to the minus 12 meters. Very, very short distance because atoms are tiny. So now let's find how we can determine the density of silver given the radius of the silver atom, given the fact that it's silver. We know the molar mass of silver. So again, here is a face-centered crystal arrangement. Density is mass divided by volume. In this case, there are 4 atoms. So find the mass and volume of a unit cell. Find volume first. So the volume of our unit cell, again, each dimension, this is A, and the third dimension is also A. So if we find the volume first, we know A squared plus A squared equals 4R squared. Because 4R is this distance here. A is this distance here. There's A, there's A. So we can solve. And again, we know the radius of the atom. The radius of the silver atom was given as 144 picometers, which we switched into meters. So it's 1.44 times 10 to the minus 10 meters. We're going to square it, multiply it by 16, divide it by 2, and then take the square root. And we now arrive at that dimension of this face-centered cubic cell. Now the volume we know is A cubed. So the volume, we're going to take this number, 4.073 times 10 to the minus 10, and cube it. That gives us a volume of 6.757 times 10 to the minus 29 meters cubed. Well, we know the face-centered cubic cell has 4 atoms. Remember, 1/8 times 8 plus 1 in the center. There's 6 faces. Half of those 6, 3 added to 1 is 4. There's 4 cells. So the mass of a single silver atom is 107.9 grams for every mole. We know that a mole is 6.02 times 10 to the 23 atoms, and we know there's 4 atoms in each of these cells. So when we do the math, we can cancel out our units, atoms cancel out, the moles cancel out, and we're left with 2 moles cancel out here, and we're left with the number of grams. There's the mass of those 4 unit cells. Well, we know the mass, we know the volume, we calculated it. Now we're ready to calculate the density of this silver cubic cell. So it's mass divided by volume. There's the volume, there's the mass. When we divide those two, we get the density. Now, I'm going to show it here. There's the answer. It's 1.059 times 10 to the 7 grams. But we want to convert this unit. So we want to convert it, the density. We want the density in grams per cubic centimeter, which is really a milliliter. We know that a liter is really 1,000 milliliters. And we know a cubic meter is really 1,000 liters. So now we can cancel our liters, cancel our meters cubed, and we end up with grams per milliliter as our unit. So we take our density and we divide it by 1,000, divide it by 1,000. And we end up with 10.6 grams per milliliter for the density of this silver crystal. All right. Now, another type of problem here, same concept. All right. So we want to find the length of a unit cell of iron. It's measured and it's found to be 286 picometers. So that's what they're giving you. We're using X-ray diffraction. What is that? It's a technique where we fire X-rays through crystals of material. The way the X-rays are deflected creates a pattern. This pattern can be interpreted into the structures, and we can figure out the length of the unit cell using that technique. So we want to know the size of an iron atom based on this data. So let's take a look. Again, now this is a body-centered cubic cell. Very important that you visualize what the diagram looks like. Now I am going to give you diagrams of these things for your exam. So we know that it's 286 picometers across. So that's the dimension here, here, and here. And again, remember the relationship between A, B, and C, the diagonal that goes from one side to the other. Why is that important? Because we know 4 atoms fit across there. So if we know C, we know what R is because 4R equals C. So we did this calculating earlier. We can say from, again, this is the face on the side here. They're showing it on the bottom. A squared plus A squared equals B squared using Pythagorean theorem. B is equal to A square root of 2. And then, of course, we can look at the diagonal. It goes from one side of the cube to the other. And we know A, B, and C, the relationship there is C squared is A squared plus B squared. But we said B squared was really equal to 2A squared. So I can substitute here for B squared. And we get C is equal to the cube root of 3 times A. So it gives us a relationship again between A and that diagonal length C, which we know there are 4 atoms that go across the radius of 4 atoms. So it gives us a relationship between the radius of the atoms and a distance we can figure out. A, in this case, was given to us. All right. This shows you just where it was substituted. So the root of 3A, we said that there's 4 radii of 4 atoms here inside this body-centered cubic cell. We know the relationship. Now we can rearrange this equation to get R is equal to the cube root of 3A divided by 4. So if we know A, we know R. If we know R, we know A. We can calculate them using this relationship. And this, of course, is different for different types of crystals. So now we can substitute in R is equal to the cube root of 3 times 286 picometers divided by 4. That equals 124 picometers. A picometer, again, is 10 to the minus 12 meters. Now let's take a look here at another problem. Vanadium. It has a unit cell structure like iron. X-ray diffraction shows the unit cell dimension to be 305 picometers. What is the density of vanadium? Okay, now again, since it says it's like iron, remember iron was a body-centered cubic arrangement, not a face-centered. So we know the molar mass was of vanadium is 50.94 grams per mole. So the mass of a unit cell is 50.94 grams for every mole. 1 mole is 6.02 times 10 to the 23 atoms. And of course, we know there are 2 atoms in this unit cell. There's 1 large atom in the middle, and then there is 1/8 of an atom in 8 locations. So 1/8 times 8 plus the 1 in the middle. So there's 2 atoms in a body-centered cubic cell. They're packed in there. Not as tightly packed as a base-centered cubic arrangement that has 4 atoms. So we can figure out the mass of the unit cell by taking 50.94, dividing it by 6.02 times 10 to the 23, and then multiplying by 2 atoms per unit cell. So again, we can cancel out the moles and we can cancel out the atoms. So we get grams per unit cell because there's 2 atoms. We doubled it. Now the volume is going to be that dimension of the unit cell cubed. So again, 305 picometers is really, a picometer is 10 to the minus 12 meters. So it's 305 times 10 to the minus 12. We have to cube it. And when we cube it, we get 2.84 times 10 to the minus 29 cubic meters. Now, because there's 100 centimeters in each meter and there's 3 dimensions, there's going to be 100 times 100 times 100 cubic centimeters in a cubic meter. So when we multiply by 10 to the power of 6 cubic centimeters in a cubic meter, we can get rid of the cubic meters and change our unit to cubic. So we now know the volume in cubic centimeters. So the density is the mass of those 2 unit cells divided by the volume, which we just calculated. And we divide those 2, and we get a value of 5.96 grams per cubic centimeter from the data given for this particular unit cell of vanadium. Okay, now this is as kind of a summary of the equations we're going to be using. I'm going to give you a copy of this for your final exam. It's going to be on your periodic table. If you got a copy of that periodic table today, then you can see it there. All right, so you don't have to memorize it. These are the relationships again for the different types of cubic cells. I didn't do any simple cubic problems, but they're done the same way. You just look at the relationship between A and R, okay, is a little bit different. And we know each unit cell only has 1 atom if you want to figure out its mass. So not a stretch to figure out problems. Now, I'm going to send you a problem sheet when the test is over today or during the test. I'll send you a problem sheet. This is the last lesson. This is the 10th lesson that we've learned. So what I'm going to do now is just say, I'm going to stop recording.